Hello everyone, welcome to the YouTube channel of YourPedia and Engineer Credit Points. So I am Vinesh Sharma, your mentor of mechanical engineering. So as you know, we were doing the previous year solution of the BHEL paper, which is held on 2023. Okay, so in the last lecture we have covered the first 15 questions of the BHEL, and now in today's videos I am going to cover up the thermal engineering part. Okay, the question which are basically asked from the thermal engineering portion here. Okay, so the subject which I am going to include is the thermodynamics here, and then we are going to see some questions of the heat transfer also and the fluid mechanics part here. Okay, so all of those questions has been already asked in the previous exam of the 2023 year. Okay, so before any delay, so let us start our today's video here. So now just see the first question in this series is the saturated water vapor at 200 kilopascal is in a constant pressure cylinder piston assembly. Okay, at this stage the piston is at 0.1 meter above from the cylinder bottom as shown in the figure. What will be the distance of the piston from the bottom if the temperature is raised to 200 degrees Celsius? Okay, and some data is given to you, so you have to calculate that what will be the final distance of the piston as you are increasing the temperature from 120.23 degrees Celsius to 200 degrees Celsius. So, okay, so here you can see first of all whenever when the piston is at this particular position number A, at that point of time what will be the state of the steam inside the cylinder here is it is the saturated water vapor. Okay, so we can say the specific volume. First of all, just see the total volume of the cylinder can be written as area of the piston multiplied by this height h1, where h1 is representing the 0.1 here. Okay, and along with that we can see the total volume can be written as the mass, okay, which is present inside this cylinder multiplied by the specific volume. So this small v is representing the specific volume at the initial state. So now what is happening? So here you can see that initially we have a condition of steam as a saturated water vapor, and which is maintained at a temperature of 200 kilopascal. Okay, so if it is maintained at a 200 kilopascal, so we can see the saturation temperature corresponding to this pressure is 120.23 degrees Celsius. That means the initial temperature of the steam is 120.23 degrees Celsius here. Now what you are doing, you are basically supplying the heat into this cylinder. So now as you are supplying the heat into this cylinder, the corresponding pressure will increase. Okay, but the piston has to maintain the constant pressure. So what it is doing, it is basically expanding from position number A to position number B here. So as soon as the piston is changing its position, so here you can see the height has been changed. Let us say now the height is h2 here. Okay, and one more thing, so we don't know that what will be the state here. So here you can assume the pressure is basically constant. Okay, so this process is taking place at a constant pressure and the temperature here is 200 degrees Celsius. So that means we are moving from the saturated vapor state to the superheated vapor state here. Okay, so we can say the final temperature first of all is going to be 200 degrees Celsius here in this case. Okay, and if you find out the final volume, the V2 can be written as area of the piston multiplied by the new height h2 here. Okay, which can be further written as the product of mass multiplied by specific volume. Okay, so if you just simply take the ratio of these two terms, you will find the h1 by h2 is going to be equal to v1 by v2 here. Now what is the value of h1 here? The value of h1 is given to you as 0.1. The value of h2, that is the distance of the piston from the bottom, you have to calculate. That is you have to calculate the value of the h2 here, and this will be going to be equal to, this is going to be equal to v1. Now here you can see initially the water vapor is in this saturated vapor state, so we can say the specific volume initially is going to be 0.88 meter cube per kg here. Okay, so we can directly put 0.88 and the value of the V2. So here at the final condition the temperature is 200 degrees Celsius corresponding to 200 kilopascal. So we can say it is in the superheated state. So here in this case the specific volume of the superheated water vapor is also given to you, which is given by 1.1 meter cube per kg here. So just put this value here. Okay, so if you solve this expression you will get the final value of the h2 here. Okay, so here the answer will come out to be around 0.125 meter here. Okay, just do the calculation and you will get your answer. So that's a very simple question. Okay, you just have to do the basic calculation here in this case. Now the next part is, the second question is, for an ideal Otto cycle, the T1 and T3 are representing the lower and the upper limits of the cycle here. What will be the compression ratio R for the maximum work output for this cycle here? Okay, so here we have to calculate the value of the compression ratio for maximum work output. How do you proceed in this question here? So if you see, sorry, just wait a minute. Yeah, so if you see in this case, now the Carnot cycle is shown like this here. Here we have 4 processes. The 2 processes are the constant volume heat addition and constant volume heat rejection, and there are 2 isentropic compression and isentropic expansion in there. Okay, so here I can say the 1, 2, 3, 4. This is the PV diagram of the Otto cycle. Okay, and you are performing in this way. So here you can see simply the work done can be calculated as, so first of all, if I write down the formula of the efficiency is nothing but it is equal to work upon heat supplied, okay, which can be further written as 1 minus 1 upon R to the power gamma minus 1 here. Okay, so that is the base general expression of the efficiency of the Otto cycle here. So in this case you can see the work done can be written as Q 1 minus R to the power gamma minus 1 here. Okay, and we already know the heat addition take place at a constant volume in the case of Otto cycle. So therefore I can write the efficiency formula, sorry, efficiency nahi, therefore we can write the work formula can be written as CV into T3 minus T2 1 minus R to the power gamma minus 1 here. Okay, that is how you can simplify this expression here. So now if you see the process number 2 to 3, sorry, process number 1 to 2. So if you see the process number 1 to 2, I can simply write T2 by T1. See, 1 to 2 is taking place isentropically. So we can write the T2 by T1 is going to be equal to V1 by V2 to the power gamma minus 1, and the ratio of the total volume by the clearance volume is representing the swept compression ratio here. So we can write that T1 is going to be equal to T1 multiplied by compression ratio to the power gamma minus 1 here. Okay, so use this value of T2 in this final expression and you will find the W is coming out to be CV T3 minus T1 to the power multiplied by R to the power gamma minus 1 minus 1 upon R gamma minus 1 here. Okay, that is the expression you are going to get in the case of work here. So here if you find further simplified further, you will see the work done is coming out to be around T3 minus T3 upon R to the power gamma minus 1 minus T1 R gamma minus 1 plus T1 here. Okay, so this will be the final expression for the work done in terms of T3, T1 and compression ratio. So now what do you want to find out? You want to find out the value of the compression ratio for maximum work output. So here you can see, here in this case the CV has been constant with respect to temperature, the T3 and T1 are already constant. Okay, and here I am assuming the air as an ideal gas, so that means value of gamma is also going to be constant here. Okay, so there is only one parameter which can vary, that is the compression ratio here. Okay, so we can say for maximum work output, you can write the dW by dR has to be, the differentiation of work with respect to the compression ratio has to be equal to 0 here. So you are just simply differentiating this term here. So here you can see that differentiation of the T3 is going to be 0. The differentiation of R to the power minus gamma plus 1 here, it will come out to be as, okay, just simplified further. So it will come out to be as R minus gamma plus 1 here now. Okay, so here you can see the it is coming out to be minus gamma plus 1 R minus gamma here, then the differentiation of this term will come out to be as gamma minus 1 R gamma minus 2 here plus 0 here. Okay, and you have to equate it to 0. So you have differentiated this entire term with respect to compression ratio and you have equated to 0, and from this equation you have to calculate the value of the R here. So if I simplify it further, here you will see the answer is coming out to be as T3 gamma minus 1 R divided by R to the power gamma is going to be equal to minus T1 gamma minus 1 R gamma minus 2 here. Okay, so you are going to get this particular expression here. So now simplify it further. So this will be the expression you are going to get here in this case. Okay, just simply cancel out this term and you will find T3 by T1 is going to be equal to R twice gamma minus 1 here. Okay, so we can say the value of the R is coming out to be around T3 by T1 1 to the power 1 divided by 2 gamma minus 1 here. Okay, so here you can see this will be the final value of the compression ratio for corresponding to the maximum work output here. Okay, R equal to T3 by T1 to the power 1 upon 2 gamma minus 1 here. So here you can see, if you check in the options, you will find the option number B is going to be the correct one here. R equal to T3 by T1 to the power 1 upon 2 gamma minus 1 here. So option number B will be the correct answer of this particular question here. The next part is, which of the following fuel responsible for the fire categorized as a class D fuel here? See, there are different classes to categorize the fire here on the basis of the combustible material here. Okay, so whenever we are defining the class D fuel, there the combustible material is basically consists of some metals here like aluminum, zirconium, like that. Okay, so option number D is going to be the correct one here. Okay, generally there are different classification. We have a class A, class B, class C and class D, and in all the classes the combustible material is different here. Okay, so that you have to remember only. Next part, van der Waals equation for a real gas may be written as, the simple expression of the van der Waals equation is being asked. So a simple expression is given by P plus A by V square multiply by V minus B is equal to RT. So this is the final expression where you include the parameter A by V square and B. A by V square is there to include the force of cohesion, where B is included to represent the compressibility effect here. Okay, so we can say the option number A is going to be the correct one here. Next part, the dead state of a system. See, dead state of a system is that system where the total kinetic energy, or I can say the total system has been come into the equilibrium state. Okay, there will be a mechanical equilibrium, there will be a thermal equilibrium, as well as there will be a chemical equilibrium. Okay, and corresponding to that condition we have a zero velocity, along with that we have a zero minimum potential energy here. Okay, so option number B is the correct one here. Zero velocity, that is the zero kinetic energy, along with that we have a minimum potential energy at that particular condition. Next part, a rigid closed vessel contains 4 kg of refrigerant at a pressure of 200 kilopascal having the dryness fraction of 0.25 here. Now what will be the volume of the vessel, and some data is given to you. So what do you want to find out? You want to calculate the value of the volume of the vessel here. Okay, so first of all, here you can see we have been provided with the value of dryness fraction. That means initially the refrigerant is in the wet mixture here. Okay, it is basically a combination of liquid as well as the vapor here. Okay, so we can say the total volume can simply be written as the mass multiplied by the specific volume. And how do you calculate the value of the specific volume for the wet mixture? That is a simple relation here. So we can say V is going to be equal to Vf plus dryness fraction multiplied by Vg minus Vf here. Okay, so that is the expression. So if you just put out the values, let me directly write it down. So here you can see the mass is given to you 4 kg. Okay, Vf is given to you 0.0075, that is the specific volume of saturated liquid. Dryness fraction is given to you as 0.25 here, and correspondingly the value of Vg, that is specific volume of saturated vapor, is given to you as 0.1 here minus 0.0075. Okay, so the simple expression you have to solve here. So option number C will be the coming out to be the correct answer here. Here you will find the answer will be 0.1225 meter cube, and if you convert it into the liquid into the liter, your answer is 122.5 liter here. Okay, just remember that, because 1 meter cube is nothing but it is equal to 1000 liter here. Now the next part is cryogenic is related to the, cryogenic is related to the maintenance of the very low temperature here. Okay, it can be around 50 Kelvin to 100 Kelvin. So we can say the cryogenic is related to the behavior and the production of materials at a very low temperature, approximately below 120 Kelvin here. Okay, so option number C is the correct answer. That is a basic simple question here. Next part, which of the following is correct? For the same compression ratio and the same heat rejection, diesel cycle is more efficient than Otto cycle. For the same compression ratio, for the same compression ratio, for the same compression ratio. So always remember, whenever you are comparing the Otto cycle with the diesel cycle, and whenever the compression ratio is same, in that case always the Otto cycle is going to be more efficient than the diesel cycle. But in actual scenario, if you see, the compression ratio of the diesel cycle is much larger as compared to the compression ratio of the Otto cycle. So we can say in practical condition, the diesel cycle is more efficient as compared to the Otto cycle here. Okay, so here you can see, if you are comparing at the same compression ratio, then always the Otto cycle is going to be more efficient. So the option number B is going to be the correct answer here. Why so? Because here the diesel cycle is more efficient, that is incorrect here. Okay, and the same way the option number C is also incorrect, and option number D is also incorrect here. So that means the option number B will be the correct answer of this particular question here. Next part, a cyclic heat engine operates between a source temperature of 900 degrees Celsius and a sink temperature of 35 degrees Celsius, and you have to calculate the least rate of heat rejection per kilowatt output of the engine will be. Okay, so that means if the engine is operating between a temperature limit of 900 degrees Celsius and 35 degrees Celsius, and the engine is having a capability of producing 1 kilowatt net work output from the system, so you have to calculate the minimum rate of heat rejection. Okay, so always remember, whenever you want to calculate the maximum work output from the system, or whenever you are calculating the least rate of heat rejection, you have to assume that the engine is a Carnot engine, or I can say it is a compressible, completely reversible engine here. Okay, so in this case you can write the efficiency of the engine will be 1 minus TL by TH here. Okay, and that will be equal to work upon heat supplied. Okay, so in this case, if you see, lower temperature is given to you 35 degrees Celsius, that means 308, and the higher temperature is given to you 900 degrees Celsius, that means 1173 here. Okay, and correspondingly the work output is equal to 1 here. Okay, we have a unit work output from the engine. Now you want to calculate the value of the heat rejection. So from the first law of thermodynamics, I can write the total heat supplied will be equal to the summation of work output plus heat rejected here. Okay, so if you solve this equation, you will find the value of the least rate of heat rejection from the engine here, or this answer is coming out to be around option number C, that is 0.356 kilowatt. Just calculate it. Okay, so that's a very simple question here. So here the option number C will be the correct answer. Next part, a vessel of capacity 3 meter cube contains 1 kilogram mole of nitrogen at 90 degrees Celsius. Characteristic gas constant for the nitrogen is 296.9, along with that the molecular weight is also given to you as 28. Okay, and you have to calculate the value of the pressure and specific volume of the gas. So now just see, you want to find out the value of the pressure and specific volume. So here you can use two equations. Either you can use the PV equal to mRT, or you can use PV equal to N R bar T. Okay, the one relation is in the form of characteristic gas constant, and the another relation is in the form of universal gas constant. But now you can use any one formula, it's all up to you. So here I am using PV equal to mRT relation here. PV equal to mRT relation here. Okay, so here you can see P is representing the absolute pressure, V is representing the volume, M is representing the mass of the nitrogen, and the R is representing the characteristic gas constant here. Okay, and T is representing the temperature here. So in this case you want to find out the value of the P here. Okay, So here I am just putting the values. So first of all, the total volume is given to you as 3 meter cube. Okay, the value of characteristic gas constant is given as 296.9 joule per kg Kelvin. The temperature is given to you as 90 degrees Celsius, that is 363 Kelvin. Okay, now you have to put the value of the mass. The mass is not given in the question. Okay, if you just read out the question very carefully, here in this question it has been provided that the number of mole is equal to 1 kilogram mole here. Now what is the meaning of mole here? Actually the 1 mole of substance is representing the amount of mass itself. Okay, so if I am saying that we have a 1 mole of nitrogen, that means the 1 mole of nitrogen is corresponding to 28 gram of nitrogen here. Okay, and this 1 mole of nitrogen is consisting of Avogadro number of particles here, that is 6.022 into 10 to the power 23 number of particles here. So here if the number of moles is equal to 1 kilogram mole, so we can say here we have 1 kilomole of nitrogen, then we can say here we have 28 kilogram of nitrogen here. Okay, so in that case the mass will be 28 here. So here if you solve this expression, you will find out the value of the final pressure and it will come out to be around 10.06 bar here. Okay, just calculate this and you will get this final answer. So you will have your answer in the simple Pascal. You have to convert this into the bar here. Okay, and the next thing is you have to calculate the value of specific volume. That is a very simple part. So here you can see the specific volume is nothing but it is represented as the total volume divided by mass here. So total volume is given to you as 3 and the mass is given to you as 28 kilogram. Okay, so if you solve it, you will get your answer as 0.107 meter cube per kg here. So that will be the specific volume of nitrogen here. Okay, make sure that if you are using this particular relation PV equal to MRT, PV equal to MRT, in that PV equal to NR bar T, in that equation you have to specify the number of mole is going to be equal to 1. Okay, and if you are putting the number of mole as 1 here, then you don't have to use the characteristic gas constant here. Here you have to use the universal gas constant, that is 8.314 multiplied by 10 to the power 3. Okay, so if you solve this, you will get the same answer here. Okay, so that is the only thing which you have to take care in this question here. Now the next part is, so here you can see the option number D will be the correct answer here, 10.06 and 0.107 meter cube per kg here. Now the next part is the irreversibility of a process is due to the dissipation of the work which lead to the increase in internal energy of the system. See, in this case, in this process the irreversibility is taking place due to the dissipation of the work here. That means some work is getting lost here. Okay, so we can say that here we are having the irreversible work present inside the system. So basically we can say this lost work or the irreversibility work is nothing but it is a type of mechanical irreversibility here. Okay, so the option number A is going to be the correct one answer here. The first one is the option number A is the correct one answer here. The next part is a very long rod of diameter 25 millimeter, thermal conductivity 400, extend from a surface at a temperature of 121 degrees Celsius and the temperature of the air is 25 degrees Celsius. The convective heat transfer coefficient is given to you as 9 watt per meter square Kelvin and you have to calculate that what will be the heat loss from the rod here. Okay, so just read out the question very carefully. It is specifically mentioned that the rod is very long. That means it is basically a question from the heat transfer. Okay, specifically from the chapter fins here, and here it is asking you to assume the fin as a infinitely long here. Okay, we have an infinitely long fin over which the heat is transferring here. So we can say in this case, when the fin is very infinitely long, the heat loss can be calculated by the particular formula HPKA delta T here. Okay, so this is the actual formula in this case. So you just have to put the values into this expression and you have to solve the final answer. So here in this case you can see the value of H is given to you as 9. Okay, now what will be the P here? P is representing the parameter. So let us suppose if you have this this rod, and this rod is having a diameter d, so I can say the P is going to be equal to pi d here, the parameter of this particular surface here. Okay, and correspondingly K is representing the conductivity, A is representing the area of cross section. A is representing this particular area of cross section here. Okay, so here I can say the A is equal to pi by 4 d square here. Okay, so in this case if you see, the P is pi into 0.025, K is given to you as 400, and correspondingly area will be pi by 4 0.025 here, multiply by temperature limit, that is 121 minus 25 degrees Celsius here. Okay, so if you solve this part you will get your final answer. So that is a very simple case, direct formula based question. Okay, and if you solve this you will get your answer as 35.7 watt here. Okay, which will be equivalent to around 36 watt here. So this will be our final answer. So the option number C is going to be the correct answer of this question here. Now the next part is, what will be the rate of heat transfer per unit area through a copper plate 45 millimeter thick, whose one face is at a temperature of 350 degrees Celsius and the other face is at a temperature of 50 degrees Celsius here. So here we have a copper plate whose one side is maintained at a temperature of 350 Kelvin and the other side is maintained at a temperature of 50 degrees Celsius, and the corresponding thickness of the plate is around 45 millimeter. 45 millimeter. And what do you want to find out? You want to find out the value of the rate of heat transfer. So here in this case the rate of heat transfer can be written as minus Ka dt by dx here, and if you perform the integration the final expression will come out to be as Ka T1 minus T2 divided by L here. Okay, so just put all the values here. So thermal conductivity is given to you as 370, corresponding area, here the unit area is given to you, and the temperature limits are 350 minus 50 divided by thickness is given to you 45 millimeter, that is 0.045 here. Okay, so if you solve this you will get your final answer as 2.466 into 10 to the power 6 watt per meter square. That will be the final value of the rate of heat loss through the system here. Okay, so option number B is going to be the correct answer of this part here. So that's a very simple question. Next part, velocity for a two-dimensional flow is given by, what will be the velocity at a point 1.2 after 2 seconds. So basically there is some error in this question because the question is incomplete here. Okay, so this is basically an objectionable question here. Okay, so you can skip that part. The next part question is, which one of the following force is a body force? So you already know that whenever you are doing the analysis in the fluid mechanics, okay, whenever you are studying the fluid dynamics part, here we have different equation of motion. We have a Euler equation of motion, then we have a Reynolds equation of motion, then we have a Navier-Stokes equation of motion. Okay, in all the cases we are considering some forces here. Like in the case of Euler equation of motion or Bernoulli's equation of motion, we are considering the inertia forces. Sorry, it is not an inertia force, it is a pressure forces as well as the gravity forces here. Okay, and gravity force is also known as the body forces here. But whereas whenever you are studying the Navier-Stokes equation of motion, there you are considering the pressure forces, gravity forces, along with that we have a viscous forces. Okay, and whenever you are considering the Reynolds equation of motion, there you are considering the turbulence forces also. Okay, that means in the case of Reynolds equation of motion we have four forces. The first one is the pressure, then we have a gravity, then we have a viscous, then we have a turbulency force. Okay, so here you can see the body force is nothing but it is a gravitational force. So option number B is going to be the correct answer here. Next part, what will be the state of body if the position of metacentre remains lower than the center of gravity here? So always remember, whenever you are considering whenever you are studying about the stability of any system, here in the case of floating body we always assume that whenever the m is above g, okay, the body is in the stable condition. That means if the value of the metacentric height gm is coming out to be positive here, so we can say it is a stable here. Okay, and when the value of the metacentric height is 0, then we say that it is at a neutral position here. Neutral position mean the M and G are coincide to each other here. Okay, basically it is coinciding, and when the M is going to be below the G here, then we say it is an unstable equilibrium here. Okay, so here in the case of unstable, the value of the metacentric height is going to be negative value here. Okay, so GM is going to be negative in this case here. So option number C is going to be the correct answer of this particular part. Next part, the heat exchanger effectiveness is defined as the difference between the actual heat transfer and the maximum possible heat transfer. See, whenever you are defining the effectiveness of the heat exchanger, effectiveness is defined as the ratio of the actual amount of heat transfer which is taking place over the heat exchanger to the maximum possible heat transfer which can take place to the heat exchanger here. Okay, and how do you calculate this formula here? So here the effectiveness is calculated as MC. You can calculate the actual amount of heat transfer either by from the hot fluid or either from the cold fluid here. So here I am just writing this simple formula. So here you can see this formula is basically the actual amount of heat transfer is basically written for the case of hot fluid here. Okay, you can also calculate this value of actual amount of heat transfer from the cold fluid also. So it will be MCCC TC naught minus TCI here. Okay, and what will be the maximum value of the maximum possible heat transfer there? The maximum possible heat transfer is always calculated by multiplying the minimum heat capacity. The minimum heat capacity can be anything between these two fluid here, correspondingly multiplied by maximum temperature difference. Maximum temperature difference, that is the maximum highest temperature minus minimum lowest temperature here. Okay, THI minus TCI. So that is the basic formula of the effectiveness of the heat exchanger here. So in this case, the option number C is going to be the correct answer, the ratio of the actual heat transfer to the maximum possible heat transfer here. Okay, so that is for today's video here. So here we have covered all the thermal part here, okay, which has been asked in the BHEL 2023 exam here. So here in this series you can also see there are some questions here. Okay, and one more thing you can also observe here. So whenever we are doing some numerical questions here, like in this case, we have been provided with some extra data here. Okay, the assumption they have provided you the value of the pi square. They have asked you to assume the value of pi square. That means the calculator is not going to be provided to you here. Okay, so maybe the same scenario is going to be follow this year also. Okay, so you have to practice all the numericals without calculator. That will be much better for you. Okay, so that is sufficient for today's video here. So now in the next video I am going to cover the remaining portion here, and in which I am going to cover the theory of machine part here. Okay, so thank you very much.